Hello everyone, my name is Ned Dimitrov and today I'll tell you about optimization of targeted epidemic intervention strategies. This is joint work with Sebastian, who's a graduate student at UT Austin, Nathaniel, who works for the CDC and Cornell University, Babak, who works for the British Columbia CDC, and Lauren, who's a professor at the section of integrative biology in UT Austin. So here's the basic problem we'll discuss today. It's midsummer in the United States, and swine origin influenza has just come into the country. The federal government has already released 31 million antiviral courses to the states and the cities inside of those states to use to combat the epidemic. In addition, the government has 50 million antiviral courses in warehouses around the country. And the goal that we're going to discuss in today's talk is how to compute explicit antiviral release schedules to delay the disease spread until vaccines are available. And in specific, we'll be thinking about releasing these 50 million courses available in the national warehouses. So for the rest of the talk, we'll do the following. First, I'll present a U.S. national scale model that we'll use to evaluate these release strategies. We'll define the optimization problem and describe an optimization algorithm we'll use to solve it. And we'll look at the results and some concluding remarks. So we'll start our disease model with a simple compartmental model. So this compartmental model is going to have compartments for susceptible, latent, two kinds of infectious compartments, asymptomatic and symptomatic individuals, and resistant individuals. And what we're going to do is we're going to combine that compartmental model with an intercity network model. So this intercity network is populated using data from the U.S. Census Bureau and from the Bureau of Transportation Statistics. In this picture, each circle represents a city, and the size of the circle is proportional to the city's population. And the thickness of a line collecting two cities is proportional to the number of daily travelers between those two cities. So you can see some thick lines here in the northeast. And what we're going to do is we're going to have discrete event transmission between cities, but we're going to have an individual compartmental model inside of each of the cities. And the reason that we had those two compartments for symptomatic and asymptomatic infectious individuals is because only symptomatic infectious individuals are going to seek antiviral treatment, and also in our model we're going to have the fact that symptomatic infectious individuals don't travel. So again, here's the setup for the problem. 31 million antiviral courses have already been released and are available to the states. 50 million courses are available in the national stockpile, and we want to compute these explicit release schedules. So to do this, what we're going to have is the availability to release discrete quantities of antivirals every month. For example, 50 million, 25 million, 10 million, and so forth. And each time we release a quantity, in addition to selecting how much, we'll be able to select whether this distribution is proportional to population, which we call pro rata, or proportional to the current prevalence in the cities, which we're going to call prevalence-based distributions. So when somebody comes to you with an optimization problem like this, you might go about formulating it as follows. Imagine that the sequence R1 to RD is the release schedule we take. So R1 would be both how much antivirals we decide to release in the first month and whether that's release proportional to prevalence or proportional to population. R2 is the same for the second month, both how much and whether it's proportional to prevalence or proportional to population. Then we have a simulator which basically takes as input this release schedule and evaluates how well it performs under a particular scenario of the epidemic. So this simulator is random, so it really returns a particular draw from the distribution of a random variable. And what we're looking for is the best schedule, the schedule that maximizes the expectation of whatever the simulator returns. And just to put things into context, you can think of the simulator as returning the expected number of people that don't get sick. So that's something that we'd like to maximize. So there are many algorithms you could use to explore the space of solutions. And what we're going to do is use a recent algorithm called UCT. So let me tell you about the building blocks of UCT. The first building block is to set up our entire policy space in terms of a policy tree. So the way that we're going to do this is we're going to start with a root node, and the edges out of this root node are going to represent the things that we can do in the first month. So for example, release 0 antivirals, 1 million, 5 million, and so forth. Now each of these nodes is going to have some edges that come from it as well, and these are going to represent what we can do in the second month. For example, release 1 million antivirals. And so a path through this tree corresponds to a particular release schedule. So for example, the path in red corresponds to releasing 10 million antivirals in the first month, 1 million in the second, and 5 million in the third. And what we'd like to do is really find the path that gives us the best response based on our simulator. So a naive algorithm to do this would be to sample every path many times, and then just pick the path that gives you the best results. However, the basic question that we have is, can we sample paths more intelligently? Because there are many, many paths on this tree, and so sampling every one would take forever. And that brings us to the second building block of the UCT algorithm, which is called the multi-arm bandit problem. So imagine that we have 6 slot machines, and we don't know the payoff distributions of these 6 slot machines ahead of time, but we have a fixed number of rounds to play these machines. The basic question is, what sequence of machines should we play so that we maximize our profit? In other words, we have to learn the payoff distributions as we play. So it turns out that the answer to this basic multi-arm bandit problem, or at least one answer, is the upper confidence bounds interval. And it works as follows. In each round, we're going to select the machine that maximizes both the estimated mean of the rewards that we've seen from that machine at that time, plus a weight. And this weight is basically going to be a stand-in for a distribution-independent upper confidence bound. Essentially what's happening is as the rounds increase, these weights also monotonically increase. This makes sure that we sample machines that we haven't sampled in a long period of time. So the way that we're going to combine these two building blocks into the UCT algorithm is as follows. So let's just forget about these lower levels of the policy tree for now and just concentrate on the first level. So here we have 6 choices of strategies that we can do in the first time step. So what we're going to do is we're going to stick a bandit algorithm in this root node, and this bandit algorithm is going to tell us which one of the edges we should select in this particular simulation round. And then the way that we're going to extend this to selecting a path through the whole tree is by sticking a bandit algorithm on every one of the nodes of the tree. And so all of the sequence of bandit algorithms is going to help us select a particular path through the tree, which we can then stick into the simulator. And the basic idea of this is that the bandit algorithms focus simulations on well-performing subtrees of the original policy space. So this algorithm doesn't give you any magical things that you couldn't get before. So for example, it's easy to show that finding the best path in general is an NP-hard problem. However, it is known that this algorithm performs very well on well-behaved trees. And in particular, the algorithm guarantees us to find an optimal solution eventually. In other words, if we run this for long enough, we'll be able to find out the optimal path. So let's go back to our problem. We're going to populate our simulator as follows. First, we're going to use early estimates of the disease parameters. We're going to set R0 to be 1.6. We'll have a 3-day latent period and a 2-day asymptomatic infectious period. And we're going to have a 6-day total infectious period. That's both asymptomatic and symptomatic. Again, we have 31 million courses already distributed and 50 million courses for which we're trying to compute a release schedule. And we're going to assume that antivirals are 80% effective for people that take them. And 2 important parameters in considering the answers to this problem is first the rate of uptake, which is the fraction of infected individuals that actually seek antivirals. And then the second is the rate of wastage, which is going to be misuse or misallocation of the released stockpile. So these are the kinds of results that we see from the optimization. In this graph, let me just tell you how to read it. On the horizontal axis, we have time. So each one of the columns represents a month. And on the vertical axis, we have rates of uptake ranging from 0 to 1. And in each of these squares, or each of these lines, gives us a policy for a particular value of uptake. Now, all I want you to get from this picture is that when we look at pro rata, which is population-based releases versus prevalence-based releases, population-based releases tend to come out more. So there's more blue in this picture than there is red. So now let's look at the same optimization when we focus just on population-based releases. And what we're going to have over here on the right-hand side is basically what fraction of the time the Bandit algorithm selects each one of the edges from the root node. So they're exactly those 6 edges from the root node, 0 antivirals, 1 million, 5 million, 10 million, and so forth. And the amount of gray or black represents how much that particular edge was chosen. So as you can see, when the rate of uptake is 0, basically each of the actions performs equally well. So the algorithm doesn't focus on any one of them. The reason for this is because nobody's seeking antivirals, the rate of uptake is 0, and so what you actually do doesn't matter. As we increase the rate of uptake to about 20%, what we see is that enough people are going to seek antivirals that we need to make sure that antivirals are available for them. And that's why these policies that make sure to release the antivirals, these high release policies of 25 million and 50 million, tend to be selected more. As we increase the uptake further to 45% or 50%, it becomes important that we release the antivirals at the right time to make sure that people who are actually sick with the disease are the people who get the antivirals. And that's why what happens is you can see that these release strategies get spread over time for these uptake values. And the lower releases of 0 million, 1 million, and 5 million become selected more highly by the algorithm at this time. And again, as uptake increases further, the epidemic ends up to be largely controlled by the original 31 million courses of antivirals already available, and that's why what we do ends up not mattering that much. And so here's a performance of the schedules that we've computed. So in this graph shows on the x-axis the rates of uptake, again from 0 to 100%. And on the y-axis, it's the number of people that were ultimately infected in the first 12 months of the epidemic. And in particular, I want to bring your attention to 3 policies represented here. One is the optimal policy when we allow both population-based releases and prevalence-based releases. The second is the optimal policy when we allow only population-based releases. And the final is the optimal policy when we assume that there's no wastage. And what you can see is that all 3 of these policies perform exactly the same. And that gives us the following take-home messages. First, that we can eliminate the effects of wastage with careful release. The reason for this is because we saw that the policy when there was no wastage performed exactly as well as the policies when there was wastage. Second, we can see that prevalence-based releases are unnecessary. The reason for this is because when we do both prevalence and population versus just population, they perform exactly the same. In other words, with just population-based releases, we can get the same kind of results as we can do with both prevalence and population releases. Finally, it turns out that the strategy of releasing 5 million courses monthly is an excellent strategy for this particular scenario. This, of course, isn't true if we change the parameters of the disease. But some of the bad news is that at least for swine origin influenza, the measured rates of uptake are around 20%. So when we go back to this graph, at 20%, antivirals are just not that effective. And so ultimately, if we'd like antivirals to have a bigger effect, we have to somehow get up the rates of uptake. So this brings me to the conclusions and future work. So first, we've built the basic optimization architecture in this project into the epidemic disease control system, which we call DICON. You can find out more about DICON from another talk on my website or from a recent paper we've released. We're also doing more studies on antiviral releases. In particular, we're considering demographic splits of the population and prioritization. For example, should we reserve some of the stockpile, for example, for pregnant women who might be more at a greater risk from the flu than other population groups? We're also studying prophylaxis. Should we use antivirals for that? And also, should we somehow pre-distribute antivirals to people in their homes so that they can immediately take them when they get the flu? Thank you very much for your attention.